Wonderful. Yeah, turn your turn your videos off. Thank you. And make sure your mics are muted also, please. Good. Okay. Oh, no, I don't want that in the corner. There we go. All right. So in this unit, we are going to be learning about logs and exponential graphs. Okay. In the past, when we talk about exponents, what we are talking about is a function f of x where, oh, sorry, I just got to adjust my screen here. A function f of x where the base is a regular number and the exponent, sorry, our base is a variable and our exponent is a regular, oh my gosh, my words. Okay. F of x equals x to the 3 or ab squared or 2y cubed or something like that. Okay, so these are examples of functions that we have a base that is either a variable or a constant number, and the exponent is always a regular number. So it's an integer essentially. Okay, these are the exponent laws that we are used to, that we have studied, and that you were supposed to practice in lesson 1. And what we're going to do in this unit starting today is now we are going to have a function where the base of the function is a number and the exponent is now the variable. So the base doesn't change, but the exponent is a variable number. So these are the properties that we are graphing. Okay, so by definition, here's the official definition of an exponential function. Okay, and it is defined for b greater than 0, but cannot be equal to 1 because 1 to any power is 1. That just gives you a straight line, right? And x can be any of the real numbers. Okay, so for example, let's graph y equals 2 to the x. So for example, if we have, we'll do some negative numbers, some positive numbers. Let's go from -4 to 4. -4, -3, -2, -1, and then all the way to 4. Okay, so when we go to graph, what is the y of this function? What I'm saying is 2 to the -4, 3 to the, or sorry, 2 to the -3. Right? And using our exponent rules, if you have something with a negative exponent, that is the same thing as writing 1 over 2 to the 4, and now the exponent is positive. Right? So if you have a negative exponent at any point, it just means you need to flip where it is. If you have a numerator with a negative exponent, that means it belongs in the denominator. If you have a denominator with an exponent that's negative, that means it belongs in the numerator. Okay, and so I'm just going to simplify this as a fraction, 1 over 16. And then the 2 to the -3 is just 1 over 8. And this is 1 over 4. And this is 1 over 2. And then what if I put 0 in the exponent? It's 1. That's right. Anybody know why it's 1? Yes, but why is it that when you have something to the exponent 0, it's 1? Anybody know? Do we need to do a quick aside? Take a look at this. 2 to the 0, we know this is 1. A visual representation would be this. What if I had 2 to the 2 divided by 2 to the 2? Using my exponent laws, this is 2 to the power of 2 minus 2, which equals 2 to the 0. And we know from our division rules that when we have same number in the numerator and the denominator, it goes into itself one time. So that's why this law is true. Okay, 2 to the power 1 gives me a 2, then a 4, then an 8, then a 16. And hopefully you can kind of see the symmetry here. When you have negative exponents, it is the reciprocal of when you have the positive exponents, meaning the numbers are the same, but they're under a 1 if the exponent is negative. And you can also hopefully notice that as we get more and more negative, we are going to get closer and closer to what value? If I have 2 to the negative 5, 2 to the negative 10, 2 to the negative 100, what number am I approaching as I write these fractions out? Closer to 0. And as my exponents get bigger in the positive direction, I'm getting closer to infinity, right? I can have 2 to the power 100, 2 to the power 1000. It's just going to keep getting bigger and bigger and bigger. So is there an exponent that I can put in place of x so that I have y equals 0? Is there an exponent that exists that I can put in to make it 0? 2 to the power of something is 0. Can I make it happen? You can either nod your head or shake your head. What do you think? Can I make it 0? I'm seeing some shaking of heads. No, I cannot. So because I cannot reach the actual point of 0, I can get very, very close to it. I can make my numbers very small, but I can never actually reach it. This means that I'm going to have a horizontal asymptote at 0. I'm never going to be able to actually touch it. So let's sketch some of these points. At 0, my y value is 1. At 1, I have 2. At 2, it is 4. And at 4, it is way up there, 16. As I go backwards, it's 1/2, 1/4, 1 something, and it gets smaller and smaller and smaller. And so hopefully you can see this is kind of the shape of our graph. It gets close to 0 but doesn't touch, and then goes off into infinity as we get larger in the positive direction. Let's make a list of some key properties. Key features of this graph. My domain is all reals. I can put anything I want into the exponent. Positive, negatives, fractions, decimals, doesn't matter. My range, however, cannot cross the 0 boundary. Therefore, it has to be greater than 0. And as long as it's greater than 0, it can also be all reals. It cannot equal 0. It cannot cross the 0. I have an asymptote at y equals 0. Cannot cross that boundary. That's the thing I highlighted in blue. I have a y-intercept. When x is 0, y will be 1. It doesn't matter what base, in fact, I have. I could have a base of 4, of 10. Anything to the power 0 is 1. So my y-intercept should always be, for a base graph, 0, 1. And then for my x-intercepts, because I cannot cross the boundary, there are none. Okay, this is a exponential growth. Exponential, oopsie, growth function. And hopefully you can see why, because it's growing as we get more positive. And the definition of an exponential growth function is the b value, or the base of our function, has to be greater than 1, right? So here our base was 2 to the power x. If your base is greater than 1, then your exponents will make it grow. On the opposite though, if your base is less than 1, so here my base is 1/2, which is less than 1, we are going to see exponential decay, means it's going to get smaller and smaller. So let's test the same values that we did in the previous example. So from -4 to +4. Okay, and the same exponent rules apply. This is the same thing as 1/2 to the power of -4. Because my exponent is negative, I need to flip this over. This is going to be 2 to the power 4, which is 16. Right? Because 1/1/2 is the reciprocal, so it becomes 2. So as soon as I put it in the denominator, my exponent is positive, but because I end up with a stacked fraction, I end up with just 2 as my number. Technically 2/1, really, but we can kind of see that already. So then this means this is 2 to the power 3, which is 8, which means this is 4, 2, 1. And then when I get to the positive exponents, 1/2 to the power 1, well, that just remains 1/2. 1/4, 1/8, 1/16. I don't have to flip it because my exponents are already positive. Okay, so this will be very similar to the above graph, but we are now going to go from big to small rather than from small to big. We still maintain an asymptote of y is 0, cannot cross that line. Okay, 1, 2, 3, 4 is somewhere up there. 1, 2, 3 is 8. Where's 8? Over here. 2 is 4, 1 is 2, 0 is 1. And then half, down, down, down. So we're looking at something like this. Okay, and this is what we call, oopsie, exponential decay. And you'll see very, very similar features to what we had in the above graph. So let's take a look at these properties. My domain is still all reals. My range is still greater than 0. Oops, gotta fix that R, sorry, there we go. Everything else is pretty much the same, right? I still have a y-intercept at 0, 1. I still don't have any x-intercepts. I still have a horizontal asymptote at y equals 0. All same as the above. So just down at the bottom of our page, I want us to compare the differences between the two equations that we just looked at. y1 was 2 to the power x, and y2 in example 2 was 1/2 to the power x. Okay, I can rewrite y2 as 2 to the negative x. Can you see how I did that? right? When we have a negative exponent, it's telling you that that 2 is in the wrong position. It should be in the denominator for the exponent to be positive, right? So I can rewrite it as a negative exponent, and I want you to see what is the difference between this and this. Negative sign, right? Now remember back in Unit 1 and Unit 2 and Unit 3, when we replace x with a negative x, when we talk about transformations, this is just identifying a reflection over the y-axis. Right? By definition, from Unit 1, if we take x and replace it with negative x, we are going to get a reflection over the y-axis. And if I zoom out, you can see everything is the same, but it's just backwards. Right? So our rules of transformations are still very much important to us. So the rule for exponential decay is that the base has to be greater than 0, but smaller than 1. Essentially, it has to be some kind of a fraction that's smaller than 1. Okay, let's go to the next page here. Okay, some definitions of a horizontal asymptote that most of you are familiar with. That the line y equals b is called an asymptote if, as the function gets closer to b, it gets closer to 0. So it gets close to b but never touches it. Okay, so when let's do a little sketch here. Let's call this the growth graph. And we'll do the decay graph here too. We're eventually going to do transformations on this, right? So we're going to be able to shift it up, down, left, right. Your asymptote will be the number it approaches but never crosses. Okay, so these two things are your horizontal asymptote. Approaches it but does not touch it. Okay, I'm going to ask you, now that we've just talked about this, and I want you to use the idea of transformation, I want you to sketch this without my help. Talk to a partner, use the graph on the first example, or sorry, the second example that we just did. Take a look at what transformations I'm asking you to do.